everyone. Welcome to the electromagnetic theory and interference course. In this magnetostatics module, let us see the application of Ampere circuit law. So we are going to see two applications in this session. So let us recall the Ampere circuit law, that is line integral of magnetic field intensity around the closed path is equal to current enclosed by the path, right? So here we are going to see the application of Ampere circuit law in case of infinite line current as well as infinite sheet current. So let us see the infinite line current. We are going to consider the line current that is long filamentary current is along the z-axis. Okay. And we are going to determine the magnetic field intensity at this point P. And we are going to consider one closed path like Gaussian surface in Gauss's law. We are going to consider one path, closed path we have to consider, right? That is known as Amperean path here. We are going to consider a concentric circle as an Amperean path. And here we have to note that my magnetic field intensity is going to be constant provided the radius of this concentric circle, this Amperean path is constant, that is rho is constant. And this path is going to enclose the whole current, filamentary current, right? And hence we can substitute the H and DL values in the Ampere circuit law. So I current enclosed is equal to line integral closed line integral of you have to consider the cylindrical coordinates, that is rho, phi and z. So since rho is constant, h rho component will be constant, and since current is along the z axis, h z component will not be present. Out of rho phi z only my h rho hz is not available. Only h phi component will be present along with this unit vector a phi cap, and we have to dot product with the differential length element. So the differential length element is going to be the arc, right? So it is going to depend on the rho radius. So rho into d phi into a phi cap. So if I dot product same unit vectors, it's going to be 1. So h phi constant, I'm taking it out and I'm integrate. Rho is also constant here. We're going to integrate over the phi. Okay. So the value of phi in cylindrical coordinates varies from 0 to 2 pi. So if I integrate d phi, I will get phi, and if I apply the limit 0 to 2 pi, I will get 2 pi here. Okay, 2 pi minus 0, that is 2 pi. So if I want to find the h, it's going to be I by this term comes to the denominator 2 pi rho into a phi cap, because my magnetic field intensity direction is along the phi axis. So that corresponding unit vector has to be represented. Hope you understood how to find the magnetic field intensity for infinite line current that is along the z axis. Right? Now let us see the infinite sheet current. Infinite sheet current is placed along z is equal to 0 plane. In that case, my magnetic field component along the z axis will not be there. That make sure from this particular point. And my sheet is going to have the uniform current density. Sheet current density is K, right? Ky into Ay, because it is the current is flowing across the y-axis. So Ky into Ay cap ampere per meter. So we are going to apply the Ampere's law to the rectangular closed path. This is the closed path taken, the path 1 to 2. It is taken above and below this z is equal to 0 plane. So the solid line shows this above the z is equal to 0 plane, and this is below it. Okay. So 1 to 2, 3 to 4, and 4 to 1. Right. This is the Ampere and closed path. As we know that the line integral of h dot dl is equal to current enclosed, since we are going to consider current flowing across the distance b, so that is going to be ky into b instead of ay unit vector. So the b comes out here, current flow, and this can be related to the current density, right? Current density k is current per that length, unit length that we have considered. So that product only is current is flowing along the y direction, magnetic field intensity cannot have a component along y direction. So Hy is 0. It's not present. And Hz is already not present because the sheet current is present in Z is equal to 0 plane. The only component of H is along the x direction. And for that we can write the magnetic field intensity as Hx into Ax cap, because in that direction only magnetic field is present for Z greater than 0. Okay, that part that we have taken, right, greater than 0. And if it's less than 0, it has to be minus Hx into Ax cap, right. Uh, so we are going to find the integral of the Ampere circuit law for the path 1, 2, 3, 4, and again to 1. So the closed part we are going to consider. So we are going to take individually. For 1 to 2, the differential length element is, see, it is along the Z axis, right? 1 to 2 and 3 to 4. So dz into Az cap for both the paths. But we saw that our H vector is in the x direction. So if I dot product, see here, if I dot product by this left hand side of this equation, if I dot product um, H into dl, yes, for is it greater than 0, that is 1 to 2 path, it is greater than 0, right? 1 to 2. No, it is less than 0 because it is flowing downwards. So greater than less than 0, minus Hx Ax dot, for dl I have to apply dz into Az. So since this dot product of different unit vectors is going to be 0, this part is 0. Similarly here 3 to 4, if you consider, it is 3 to 4 is along the positive side, so is it greater than 0? So I have to apply this part Hx into Ax dot dx z into Az cap. So here also dot product of different unit vectors will be 0. The entire over these two paths, okay, this vertical path, the answer is 0, the closed line integral. Now we have to consider the other two remaining paths. 2 to 3, if I take, what is the differential length? It is along the x direction, parallel to the x, right? So it is dx into Ax cap. And if I dot product h and dl, so 2 to 3, it is going to be the plane, it is below the plane, right? So minus hx into Ax cap dot, for dl it is dx into Ax cap. And dot product of same unit vector is going to be 1. And how this negative gone means, the limit is going to be from 2 to 3. That is from the positive x to the negative x it is going. So see, this side is negative x, right? So the overall integral will be positive only. And the length component is b. So b into hx. So for path 4 to 1, the final path, same dl is dx into Ax, since it is parallel to the x-axis. And here the region is greater than 0. So I have to consider h as the positive hx into Ax cap. So I have substituting in that line integral. Okay, what I get, a dot product is 1, and already we are getting the positive hx. And if I integrate from 4 to 1, what is the answer? It is going to be x. When I apply limit b, it is going to be b hx. So overall, sum of the integrals for the closed path, starting from 1 to 2, 3 to 4. Okay, 1 to 2, 3 to 4, 2 to 3, and 4 to 1. If you see, we get a 0 in the previous slide, and here 2b hx we got. So that we are going to equate to the current enclosed. Current enclosed, we already saw that it is for the distance b, it is ky into b. Ky into b is equated to 2b into hx. Okay, if I equate hx is half of ky. And how can I write the magnetic field intensity? It is half ky into the unit vector along the x-axis, because magnetic field intensity is finally along the x direction. So is it greater than 0? If the point lies in the plane less than 0, means it is going to be negative of the same. So general case, I can write for infinite sheet with having the current density k vector ampere per meter. I can write h vector as half of k vector cross an vector. That is, the unit vector is taken normal from the sheet current. From the sheet current, what is the normal vector? And to the point which I have to determine my magnetic field intensity. I hope you understood how to find the magnetic field intensity for infinite sheet current. It is half of the infinite sheet current density into the unit vector cross product of it.